Alright, so the next problem is related. So it wants us to calculate the volume, so volume is what I'm looking for. If the air is heated to, so this is a new temperature, so we're going to say 99 plus 273. I think this is going to be a Charles law question because it says that pressure is the same, and so volume and temperature are being compared. So that's Charles law. Charles law says that volume and temperature are proportional. In other words, as volume goes up, temp goes up also. So the equation to represent that relationship when things are changing is this. Okay, so this is a fast way to solve the problem. We know our initial volume and our initial temperature from this question, right? So the initial volume is this much, the initial temperature is this. So we can plug that in there. We want to use the temperature in Kelvin still, because that's an addition and you can't skip it. You'll get the wrong answer. So that'll be 293 down here. And on the other side, the volume 2 is what we're looking for, and temperature is 372 Kelvin. Okay, so the correct answer for this is going to be 2.8 times 10 to the 6 divided by 293 times by 372. So we end up with a very large number. I'm going to write it in scientific notation. 3.56 times 10 to the 6. And let's see, so we multiply the k and got rid of it. That means L is all that's left. So there's your answer. Now, I want to just show you what would happen if you don't convert the temperature, right? So if you do 2.8 times 10 to the 6 liters divided by 20 degrees Celsius equals something divided by 99 degrees Celsius. All right. The Celsius still cancels, so it seems like it should work, okay, but well, let's just see. So 2.8 times 10 to the 6 divided by 20 this time, times by 99. So the answer we get is 1.39 times 10 to the 7. So that's a really different answer, and it's not correct, and this is why the ideal gas law, actually all the gas laws, Charles law, Boyle's law, all of them, we use Kelvin. Okay, so it's an absolute temperature scale. Imagine if we had 0 degrees Celsius down here, you would get 0 in the denominator, which is just wrong. You can't divide by 0. The world ends. Well, not really, but you can't do it. So we have to convert to Kelvin. This doesn't work. Okay. Now there's other ways to solve the same thing. You might use what we call the combined gas law and just assume some pressure. So the combined gas law looks like this. It accounts for pressure, temperature, and volume changing. Okay. It's really the ideal gas law, just rewritten, because we know the moles aren't changing and the R doesn't change, so they kind of cancel each other out. But you could also plug it into this equation and you would get the same thing. You could also plug it into the ideal gas law, solve for moles, plug that in with your new temperature and solve for the volume, and you'll get the same thing. So there's a lot of ways to do these problems. Don't think that if it didn't match my method that you're wrong. That's not true. Okay? So the next question is about collecting a gas over water. So we talked about that process in class. We've actually seen this reaction of degrading H2O2, right? Let's try this again. So it takes 2 hydrogen peroxide and it produces, hopefully this sheet looks better on your copies than it shows up on my iPad, but here we go. Okay. The catalyst is MnO2 that goes over the arrow. It doesn't actually participate in the reaction. And, barometric pressure is the room pressure, 754 millimeters of mercury, and our temperature is 23 degrees. Okay. Okay, so this is asking about volume. It's asking how big does the container need to be. So, first let's convert pressure. And then we'll convert temperature, so everything is in the correct units. 0.992 atmospheres. And then we got temperature to convert, so let's do that. It's going to be 23.0. So I'm thinking that I'm going to need 3 significant figures. So far I have 3 on both of my data, so I'm guessing that's probably what it's going for. So that's going to be 296 Kelvin. Okay, so now I got the right units. I think I'm going to try to plug it in PV equals nRT. It tells me how many moles right here. Okay, so to find the volume, it's going to be nRT over P. I'm going to use this ideal gas law and not some other version because I need moles. I'm given moles, I got to use it somewhere, and the only one that has it in there is the ideal gas law. So we're going to go 0.25 moles times R. They gave us that R value, but I like to use one extra figure. When I have 3 sig figs, it's 4 in my constant, just to make sure that doesn't affect the rounding. And then, let's see, our temperature is 296. That's a K, I can't finish writing it very well, but there you go. And then our pressure, we figured was 0.992. Okay, so our unit, we better just check that. Moles will cancel, K will cancel over here. Oh, I forgot to write the unit, that was naughty. Atmosphere, so we get liters, so we've set the problem up correctly. Okay, so I multiply all the top, divide by 0.992, and I get 30.6 liters. So that's how big I need the container to be. Okay. So the next question, you can pause it here if you want to write that down. Okay, the next question is how many grams of hydrogen peroxide do I need? Oh, okay, so I know I need 0.25 moles of O2. So this is a stoichiometry problem. I need the balanced reaction. 1 O2 for every, where did my 2's go? 2 H2O2s. So 2 H2O2s for 1 O2. And it wants to know grams, so I'm gonna have to figure the molar mass, which is 2 times 1.01 plus 2 times 16. So that's 32 plus 2.02 is 34.04. A lot of you have the habit, when you do bother to show the formula weight, you're not showing me, but a shocking number of people keep messing that up, so I do need to see that calculation. This way I can at least award you the credit for attempting it. If you don't show me the work, then I don't know where it came from, so no credit can be given. Our answer here is that we need 17.02, which to the number of sig figs we have. Oh, we only have 2 here, actually. Oh, that's going to change our answer above. So it's just 17 grams. And this answer, the prior answer will have 2 significant figures as well. So I want to go back and change that. I didn't remember that our moles is just 2. Okay. So the next question, I just realized I forgot to do 7C, so 6C, so we're going to go back. I'll pick up with 7 in a second. So the last part of this question is to calculate the pressure of each gas based on the percentages above. So the easiest formula to use for this is the P total equals the ratio, which I wrote in the notes as the moles of gas 1 divided by the total, but it's just that chi, right? So let's say the ratio for N2 times the total pressure. Oh, wait, I messed this up. It's not P total here, it's the P of N2, so the pressure of the nitrogen, equals the fraction due to nitrogen times the total pressure. Okay, and you can apply the same thing for oxygen for all of them. So when we go back to this and we look at it, we say, okay, here's your fraction, 78.08%. We can turn that into a fraction by just, dividing by 100. So the pressure of N2 is going to be 0.7808 times 1 atmosphere. So of course that's 0.7808 atmospheres. For oxygen, the same thing applies. This time we have 20.95, so my fraction will be 295.295 times 1 atmosphere, which is 0.2095 atmospheres. The pressure of CO2, I think, is the next one. Oh no, argon is 0.93%, so 0.93 divided by 100 is 0.0093 times 1 atmosphere. So again, that's going to be 0.0093 atmospheres. And the pressure of CO2 is very, very small, 0.031. 0.031 divided by 100 is that, times our 1 again. Okay. So that's actually a pretty trivial calculation. There are other ways to do it, as usual, but they're much more time-consuming. So if I just remember this relationship, that the pressure of a gas is equal to its fraction times the total, this question's pretty easy. Okay, so let's continue with stuff. Okay, so when we've done the experiment, we measure the temperature at 23. I'm probably going to need to convert that, so I'll do that right away. So 23 plus 273 is 296 again. Apparently that was the popular temperature in the lab. It says the vapor pressure of water, so that's the partial pressure due to water, equals 21.2 torr. I'm going to convert it on the assumption that it's not the basic unit we use in gas problems. You might have noticed a theme. There's a lot of converting units to begin with, and then you just plug it in. It's pretty straightforward if you've got the right units, but if you mess that part up, it's going to mean that your answers are wrong. So the pressure of the water is 0.0279. It says 789, but I only have 3 significant figures here, so I'm going to go with that. Okay. Determine the partial pressure of oxygen in your final container. Oh, okay. So the pressure from the problem here, oh, here it is. The pressure is 754 atmospheres, which is ambient. Ambient means room pressure. We already converted that, 0.992 atmospheres. Or I could use it in 754, but I like atmospheres. That's the ambient pressure, or what you would call pressure total. Okay. So the P total equals the pressure of the oxygen, which we don't know, plus the pressure of the water, which we do know. So it would be 0. So this just boils down to some addition and subtraction. This is Dalton's law of partial pressures, right? So the pressure of oxygen plus water adds up to the total. 0.0279 atmospheres of pressure. So I'm just going to go 0.992 minus 0.0279. And so our pressure is actually, the pressure of the oxygen is actually 0.964 atmospheres. Okay? So